Well, hello, everybody, and we would like to welcome you to this discussion on sustainable pretreatment for aluminum connectors in aerospace by MacDermid Enthone. My name is Robert Collin. I am the America's Technical Manager and moderator for this event. The presenter today will be John Stripka. He is the Business Development Manager for connectors in aerospace for MacDermid Enthone. Please submit any and all questions you have in the questions box in this chat. We will do our best to answer all of the questions at the conclusion of this webinar. If for some reason we cannot get to your specific question, we will contact you via email and start our discussion. From there, everyone, thank you all for taking the time to learn about our sustainable pretreatment for aluminum connectors. John, this presentation is all yours.
All right, thanks, Rob. Thanks for the introduction. Once again, thank you everybody for attending our webinar. Today we're going to go over pretreatment cycles for aluminum connectors used in the aerospace industry. Okay, before we get into the technical part of the presentation, MacDermid Enthone has created a group of technical experts for our connector team for the industry for aerospace. This team has over 160 years of experience dealing with connectors, pretreatment of aluminum. We have this team located throughout the United States. We have Jim Galloway, who's located on the West Coast, Doug Hughes, Mike Vectorelli, and Doug Richard, who are located on the East Coast of the United States, and John Plowski and myself were located in the Midwest. This team is dedicated to developing process techniques and new technology to help us meet the new requirements, new specifications that exist now and that are coming down the line, down the pipeline. So we are dedicated to helping our applicators, any of the aerospace OEMs or tiers that are looking to design or develop new specifications. We're here to help and improve those processes. So before we get into the exact steps that you go through, there are some things that you have to take into account when we look at aluminum connectors. Due to the variation in the alloys of aluminum, there are so many different types. We really need to know specifically which ones we're looking at, which ones we're trying to process, because they're all going to affect the different steps that we're going to go through. Another thing, because of the different alloys, you're going to use different alloys for different characteristics you're looking at, whether it's the machinability, whether it's the hardness, whether it's some other properties that you're looking for. When we're doing this, one of the things that are very important before we get into the pretreatment process is making sure that these parts are machined properly so that there are no folded over metals, there's no burrs, there's no pitting, there's no deep scoring. Something that is typically overlooked is this manufacturing process, and it is very important, and it really affects the performance that you're going to get from the end product that you put out. So it's really important to make sure that the areas are machined and prepared properly before they come to the process line. So as I mentioned, with all the different cycles, we're going to have to take a look at which alloying constituents are in these materials, and this is going to help us to decide which steps to modify, which cleaners to use, which types of etches, which kinds of desmuts, all of these things which are going to be important for you to get a good quality deposit that are going to meet your salt spray and corrosion requirements. And the thing about this is we have cycles that we've developed through all of our experience, but even that being said, there are new alloys starting to be used. There's different types of alloys, and because of that, there is still a lot of trial and error. And what we mean by trial and error is taking these materials, using our expertise, and then doing cycles on these and testing them. And by testing them and getting the data, we can give you good cycles to use to process your individual material. So if we go and we look at the typical steps that you would use for processing aluminum, the first step you look at is basically a soak. We call it a non-etch soak. It could be a mild etch soak, but typically it's a non-etch soak that you use first. And this soak is a cleaner, as we call them. They're used to remove light soils. So you're looking to remove any machining oils, any fingerprints, any material that could have gotten on the parts during your machining process, the molding of these parts. And we're just trying to get that off the surface so that we don't have a barrier to the next steps that we're going to go through. So once we do that and we get these oils removed, we go into the next step, which is some kind of etch. I'll discuss the different types of etches in a little bit more detail. What we're doing here is we're just kind of slightly roughening the surface of the part to give you a good substrate where we have a little rough peaks and valleys so that we can get really good adhesion of the following coatings that we're going to apply to the aluminum surface. So once we've roughened up the surface a little bit, typically when this is happening, you're actually attacking the aluminum. So a lot of times the constituent alloys that are in there, they're going to come to the surface and they're going to remain on the surface of the part, because the etch really isn't designed to dissolve the alloying constituents. It's just kind of to roughen the surface. So you have these alloying constituents which are sitting on the top, and we typically refer to them as smuts or oxides. So this desmut, deox as they're called, typically that's what they're for, is to remove this material. So now you have a nice, clean, active surface, roughened surface. Everything's removed, and now you can go into the next step, which is a zincate. The zincate goes on top, basically forms a little layer of zinc on the surface of the part, and this allows the next steps to be put onto it. If you don't have this zinc layer, you're not going to get adhesion of your electroless nickel or any of the other coatings you're going to put on there. The aluminum forms an oxide so quickly that you couldn't get from the etches and everything into your plating processes and not have the oxide form, which would then affect the adhesion that you would get of the subsequent coatings you're putting on. Once you go through the zincate, typically, unless you're doing a cast part, typically you're going to go and you're going to strip off that first layer of zincate. Now, it doesn't completely strip off the entire layer. It strips down to a very micro sub-micron level of zinc on the surface, and then you put on another layer. The reason you put on the second layer is, for the most part, improves adhesion, and it also improves the grain structure of the zinc that's being deposited on the surface of the aluminum. The very first zincate is different from the second zincate, and I'll discuss that later on when I go into more depth into these steps. Then we're going to rinse, then we're going to go into either some kind of EN strike or other strike, and then the EN, or we're just going to go directly into the electroless nickel. One thing to note is that on the slide there aren't a lot of rinses put in here, but between each step there are rinses. At the end of this presentation, I have 2 cycles that we've developed that are very successful in meeting the requirements for corrosion protection and preparing the aluminum surface for a very good final finish of your metal coatings that you're going to put on. So we'll go over those in depth, but I just want you to realize that this slide is just a basic description of the steps that are used to process aluminum. So if we start looking now a little bit more in depth, we go into the cleaners. Okay, there's different types of cleaners. You can have alkaline cleaners, or you can have acid cleaners. Typically, the alkaline cleaners, they are able to remove a lot of different types of material. They have, different types of oils or machining fluids that you use in your manufacturing process. They also have very wide operating windows. You can operate them different temperatures, different concentrations. Each one of them is going to be designed or formulated to remove specific types of oils or wide ranges of oils. So there's all different kinds, all different types, and we have all of those available that you would need. When we get into, once you've used these products, the alkaline cleaners, they are a little bit more difficult to rinse. So you have to make sure that you have good rinsing steps between the soak cleaner before it goes into the mild etch. Other types of cleaners there are the acid cleaners. They do show a little advantage on cast alloys, which are porous. The acid is a little bit less aggressive, I guess I would say, than the alkaline cleaners. And they're more easily removed in the rinses. So you have this balance of, okay, which one should I use? Which one shouldn't I? And it really depends, once again, on the alloys that you have. So once we go through the cleaners, we come out, we rinse them, we have all the oils removed or all the material, foreign material removed. We can now go into our etch. And why are we going to use an etch? The etch basically removes any burrs, machining lines, fine scratches on the surface of the part, of the substrate. And this is going to help us improve our ability to get adhesion and to improve our corrosion resistance. Also, the etch is going to help us remove any oxides that are on the surface of the part. And the etches actually help us, once again, improve adhesion if you have a highly polished surface. You need that little roughness to be able to get the initiation sites for the adhesion to take hold. You want that bond, that atomic bond between the material you're putting on onto the aluminum substrate. So with that said, once again, there's different types of etches. We have alkaline etches and we have the acid etches. The alkaline etches, they contain sodium hydroxide and they are very aggressive towards aluminum. They tend to have a high rate of attack. The alkaline etches also tend to attack the aluminum more than they do the alloying constituents. So I have a slide after I talk about the acid etches, and it'll give you an example of the difference between the etches on how they attack the aluminum, the attack on the aluminum rates and the alloying constituents. But alkaline, they attack the aluminum more. Now, when you're using these etches, the alkaline etches will stay active and they'll perform to how they're supposed to, as long as the free alkalinity remains at a level that's recommended by us. If you get below that free alkalinity, they're not going to perform as well. You're not going to get the etch that you would get when you first made them. So it's important to maintain them, to make sure that you're maintaining that free alkalinity in there so that you are able to have them perform correctly. And then we can have additives which can be added to these, which can help control the etch rate, the pattern, the grain size, because we don't want to form any hydrated aluminum oxide scale. If we do, then we're going to run into issues in our next steps that are going to come down the line. Okay, so alkaline etches based off sodium hydroxide. Acid etches. Acid etches are based off of the acids, of course, phosphoric, nitric, sulfuric, hydrofluoric. The acid etches, unlike the alkaline etches, tend to attack the aluminum and the constituent alloys together, so you get a more even etch. Also, as like the cleaners, when you look at the etches, the difference between the etches, the alkaline etches are a little bit harder to rinse than the acid etches. So we tend to favor the acid etches because we tend to like the nice micro etch that we get on the aluminum when using the acid etches, and they're typically more easy to control with the amount of etch that you're putting on them compared to the aluminum etch, or the alkaline etch, sorry. So this was the slide I was talking about. So if you have your material here on the left, you have the aluminum, and then you have the alloying elements that are inside, whether it be copper, magnesium, silica. You go through an alkaline etch, what you see here is that the aluminum is attacked way more than the alloying elements. Whereas you come down here and you go through the acid etch, you're going to see it's much smoother. It's been attacked evenly, where here it's a little bit rougher. You're going to have a little rougher surface because of the alloying elements not being attacked. Okay, so once we've gone through the cleaner, and now we've gone through the etch, like I was mentioning, on the etch, after the etch on the part, there's going to be some non-soluble alloys that are on the surface that weren't attacked by the etch, that are just sitting on the surface. We call them smuts. You can easily see them. You can rub your finger across the part. Your finger is black. You have the smut that comes off. Typically, these smuts are the alloying constituents, which are the silicon, the copper, magnesium, and other things that are put in there for whatever reasons, for hardness for the machining, as mentioned before. The D-smuts or the deoxes, they're called both. They're designed to dissolve these constituents. So you want to dissolve the constituents without further attack on the aluminum substrate. We don't want to roughen that surface too much to where we're going to create pores or other issues, so that when you put your electroless nickel or your other coatings on top, you're not going to get uniform coverage. So you want to make sure that your D-smuts, your deoxes, aren't going to attack the surface anymore. But they're going to get rid of that, because you have to be able to remove with the etches, the oxide film, and then anything left on the surface, because if you don't, when you go to put your other coatings on top, they're not going to stick. You're not going to get adhesion. And once again, the type you're going to use is going to depend on the alloy. So with that being said, which one do I use? Which acid do I want to use? So if I have copper in my alloy, typically you want to use nitric acid. If you have magnesium, you use sulfuric. You have silicon, you're going to need fluoride. When you have mixtures, then you're going to have different mixtures of the acid. So if we go and we look, okay, so I have the 1,000, 2,000 alloys. What do I want to use? Well, those typically have the copper in them, so you're going to want to look somewhere between 30 to 70% by volume of nitric, and then the rest water. And the difference in the concentrations is going to be the difference in the alloys and how much material is in there. Then we go down now 2,000, 4,000. So you can see there is a little bit of overlap. The nitric acid in the water is for 1,000, 2,000. Now we go nitric acid. Now we add a little bit of fluoride, and now you start going 2,000 to 4,000. Because the 2,000, 4,000, a lot of them have silicon and they are castings. So when you look at that, now we're going 30 to 50% by volume of nitric, and then we're adding the ammonium bifluoride in there to help with the silicates that are in there. Okay, now I have magnesium alloys, or I have more castings. Once again, a little overlap, as you can see. Now we're going nitric with the fluoride, but now we're adding sulfuric, commonly referred in the industry as triacid. Once again, the concentrations can vary: 30 to 50 nitric, 20 to 30 sulfuric, 60 to 100 grams per liter of fluoride, and the rest water. These are very good for castings. For our recommendations, we would say to use a triacid when using castings. The best adhesion, the best corrosion performance we see from our experience is using a triacid on cast aluminum connectors. Now, if you're at a facility and you're like, man, I don't really want to use nitric if I don't have to, there are sometimes the ability to be able to do just sulfuric with hydrogen peroxide. Once again, you're going to have to work with your specific alloy and work with us to come up with the specific percentage of sulfuric and peroxide and in the water to come up with the one that's going to work best for you. One thing to know is that the peroxide is very volatile, so it typically takes a lot of control on that process. Once again, if you have silicates, you can add the fluoride in there to help you remove that off the surface. Now, if you don't want to use the acids, the nitrics, and the other ones, we do have proprietary products that work for deoxes. The 184 works very well. It contains iron. It can be used on a wide range of alloys. Once again, we can add the fluoride if we need to for the silicon. And then we have persulfate compounds for the copper that we can add also. It's a very good deox, and you'll see in the cycles that I recommend in the end that that's what we prefer to use, because we know to be sustainable going forward, a lot of people are looking at how can they make their processes more environmentally friendly, and this is one way to do that. Okay, so once we've taken off the soils, we've roughened the surface, we've taken off any of those alloys that are sitting on the surface that we need to remove, the oxides. Well, we have this nice, clean, active aluminum surface, but we can't just go and put the plating on there because it's not going to stick. So we're going to put a displacement coating on, which is called a zincate. And like I said before, this is going to put a layer of zinc on the surface, which is going to retard any oxide formation on the surface of the part. So then when you go into the subsequent steps, you're able to get a good bond to that zinc surface. So there's different types of zincates. There's alkaline and acid formations. I've only seen the acid formulations typically used on magnesium parts. I don't typically see them being used on aluminum. The majority, I would say 95% of the people in the industry are using alkaline zincates. Now there are two different kinds of zincates. Well, there's many different types, but from our point of view, what we find that works the best, we have non-cyanide zincates and we have cyanide zincates. The non-cyanide, as you can see, we have a couple products, one called Alumon EN and the other one Bondol CF. They work very well. If you want a cyanide-based one, you have your Bondol, your Alumon 94-8 or Bondol Special. Within these zincates, they're different. They have different alloys in them, not just zinc. There's also some other metals that are in there, such as copper or iron. They get co-deposited along with the zinc. They help refine the grain of the zincate, the grain structure. And basically you want this nice coarse formation of zinc molecules on the surface, which is going to help improve the quality of your corrosion protection when you go into your EN step or your strike after the zincate. What are the zincates made up of? Typically there's a zinc oxide, then they have sodium hydroxide, and then they have some grain refiners in there. And like I said, the zincates, they differ, but why is it so critical? Why is it so important which one I use? Why do I care what they're made of? Well, some people can have cyanide in their facilities, some people can't. So that's one variable that you have to consider when you're looking at which ones do I want to use. Also, the Zincate reactivity gives you different operating conditions, temperature, concentration, dwell time, things like that. All these things are important things when you're considering which Zincates you're going to use. So if we look at different types of Zincates, because of the different ways they're formulated for different materials, you can see that the different names down here on the bottom, they give you different adhesion properties, which give you different performances on your coating adhesion. So per the slide, you can see that the Bondol works really well for us. It gives us very good corrosion. The different bars here are the different alloys, 2024, 60, 61. You can see they basically perform the same ratios for the different alloys. So the Bondol is really a really good Zincate, and it offers us the best adhesion when looking at the processes when we go forward. So we put on the Zincate, and then we strip it off. Why do we do this? I mean, I already got the Zincate on there. I can apply the EN. Why would I want to put on another Zincate? Well, as I explained, so that the first Zincate layer goes down, and it's kind of what we call a spongy coating. It's got big crystals. It's kind of rough. It's not very smooth, but we do like to just do a single Zincate on cast parts. We typically see better results for corrosion protection and adhesion performance on cast parts with just a single Zincate. Now, when we go into this, when we're doing polished machined aluminum, we're definitely going to want to do the double Zincate cycle, as they call it, because once again, that second layer now, you have that spongy first layer, you strip it off, you leave a fine layer of zinc on the surface. Now we put it into the second Zincate, which is typically a little bit shorter time than the first Zincate. And this is going to put a finer, tighter grain structure on the surface, which then promotes a smooth, pore-free surface from your EN when you put that on to the Zincate. So here's a picture that shows a difference between the surface morphology of the Zincates. As you can see on the left here, when you do just a single Zincate, the crystals that are formed are much larger. They're less uniform. Once you strip that down and you put on the second Zincate, now you can see the grain size is much smaller, much tighter. Gives you a better surface for the adhesion of the following electroless nickel steps. So we've gone through the soak, the etch, the deox, the Zincates. One of the things that I mentioned, the rinsing. Rinsing is very important. Rinsing is very important for any pretreatment, but especially for aluminum, you want to make sure that you have DI rinses. Your DI rinses are clean. You know, if you can maybe incorporate spray rinses, that's good. Also, the extra mechanical impingement of the DI water on the surface helps remove any of the previous steps. It helps remove the cleaners. Just like if you put your hands in water, you know, if you put your hands in water and pull them out, you still have that soap film on there. If you put your hands in the water and you rub them together inside of the water, that little mechanical action helps remove that alkalinity, the surfactants that are in those cleaners. So it's important for the cleaners or the rinses to be clean so that you can get those soaks and acids and everything off in every step through the process. Cold water, not very good. Get it below 60, it doesn't rinse, it doesn't clean off the surface, it doesn't remove those steps, that the previous steps that it's trying to help you get off. Warm water just right, 75 to 90. That's the perfect range to help you solubilize any of the surfactants or anything else that's on these parts going from one step to the next. If you get your water too hot, now you can run into problems. You get it over 100 degrees. Between these steps, you can cause the surface to get oxidized, which we don't want. Before we get to the zincate, if you have these hot rinses and you form that oxide layer, you're not going to get good adhesion to that base aluminum material. If you do the spray rinses over the tank, what's that going to do? It's going to help you keep your cleaners in your tanks. It's also going to keep your next rinses that you're going to use cleaner, so you don't have to replace them as frequently. Typically, what we like to see are counterflow rinses in these things, where you're going into your dirtier rinse, then your cleaner rinse, and then you go into the next process. So it allows you to get a really good, to remove all that stuff off the surface. And I might sound like I'm beating this over and over. The reason I am is because it's very important. People think that the rinses are just, a lot of people don't consider them to be important, but I'm letting you know that a lot of our problems we see are people not using the rinses correctly or maintaining them correctly, going from one step to the next. If they don't remove off, say we have some components in the soak cleaner, we don't get them off before we go into the etch can actually set these things up on the surface. So whatever step you do following that is not going to remove it, because once it's set up, it's very, very difficult to get off. So that's why I'm stressing rinses are very critical in these processes. So once we go through the steps and we get the Zincate on, some people like to put on a strike. Some people just go directly into the Electroless Nickel. Some people like to use a conditioner, prepare the surface for once it goes into the EN. When you do this, what are you doing? Well, if you're doing a conditioner, it helps the Electroless Nickel initiate faster. This in turn gives you a nice smooth base layer of nickel going onto the surface, which then when you go into your EN following it helps improve your corrosion. What else do strikes do? Well, they protect your main Electroless Nickel solution. As you go from the Zincate into that first step, some of the zinc gets dissolved as the nickel's being deposited. So if you go into the strike, which typically is more economical to make compared to your main EN bath, you build up the zinc in there, and then after a while you dump that, make up a new one. It's much more cost effective to do that than to be dragging the Zincate directly into the EN and then dissolving the zinc in there, because as the zinc builds up, the deposit properties are affected, they get degraded, and therefore you have to end up dumping your EN bath faster than you would if you used a strike before it. The strikes help seal the substrate porosity. They also add an extra barrier underneath the Electroless Nickel, because they're already putting a layer of nickel there. And one of the things that we typically see when doing these coatings, the more layers of Electroless Nickel you put on there, we tend to see a little bit better corrosion protection, because of if your Electroless Nickel strike goes on and it has a few small micro pores. When you go into the Electroless Nickel, you have this opportunity now to cover over those pores with another layer of Electroless Nickel. And if you're going to be doing any basket or barrel work, the strikes help with getting maximum adhesion on those parts. So what kind of strikes could we use? We've already talked about the Alkaline EN strikes, the Alumon AL100. We also have an ammonia-free strike. Once again, we know that people are looking for sustainable solutions going forward, and this fits the bill, because now we don't have the chelation of the ammonia, and we don't have the smell of the ammonia, which, as we know with Electroless strikes, the ammonia level is very high, so you have this smell that is related to that. And with these ammonia-free strikes, we don't have that. We also don't have the problem now of having ammonia in your waste stream added in because of the strikes. We can also do sulfamate strikes or cyanide copper or cyanide nickel, or I'm sorry, cyanide copper or nickel strikes like a Woods or a sulfamate. When you do these, you're going to have to make sure that you go in with live entry. It's not widely used. The most typical strike used is a Alkaline EN strike. They're easier to use, easier to control. They give better performance from our experience. So we've gone through all the steps now. Now, when I'm going to talk a little bit about the two cycles that we developed, but before I go through them, I just want to give you a little background information on how they were developed. So when you start looking at cast aluminum is very porous. They seem to contain this little skin around the surface. We call it crud. It's this material that's around the surface that makes it very difficult to get good adhesion to it. So when we look at cast aluminum, we have to make sure, sorry about that. When we look at the surface, we have to make sure that we get this skin off of there. We also, because these things are porous, we want to look more at non-etch cleaners. We want to use mild acid types. We want to avoid the aggressive caustic etches, because what those are going to do, they're going to open up the pores. They're going to make them more porous. It's going to make it much more difficult for us to get good corrosion protection. So this is a typical cycle that we recommend. These are our products that we use that give us very good performance qualities, help us pass corrosion in a lot of different environments, up to 1,000 hours, even more, depending on how well everything's done in the line. As you can see, we have varying times, varying concentrations, varying temperatures. The reasons why we have these, once again, a lot of it depends on what alloy of the cast are you using. But as we go down the process, we go through our IsoPrep 740. It's a very good cleaner. It's a wide operating windows, temperatures. You can actually use this cleaner as a non-etch cleaner, or if you want a little etch when you're cleaning before you go in your acid etch, you can actually run it a little hotter. So it has a lot of variability. It's a very good cleaner. Helps us remove a lot of different types of oils. We find that this cleaner is one of our best cleaners that we have to offer. Once we go through the IsoPrep 740, you can see the two rinses. Then we go through our etch, which is we like to use acid etches. Like I said, they help to give you a little bit tighter control on the etch pattern and the amount of etch that's done. Our product that we like to recommend is MEIS aluminum acid etch. This gives us a very good fine etch along the surface of the aluminum. Once we come out of that to do our desmut, like I said, on cast products, we definitely recommend a triacid. The triacid in containing etch salts, which are the fluorides and other salts that we can use to help with the silica that's in the alloy. Once we come out of that, we go down, we go into our Bondol, our aluminum EN, which is our Zincate. Once again, different concentrations, different times. Then we go down, we rinse, we go through our strike, because like I said, on cast aluminum, we prefer just to do a single Zincate. That's where we find our best performance, our best quality, our corrosion protection that we get by just doing the single Zincate. We go into the end plate AL 100, which is our alkaline strike, come out of there, then go into our mid phos or high phos or whatever electroless nickel that you need to, depending on the specifications you're trying to meet. And then rinse, hot rinse, and then dry. So that's our preferred cycle for cast aluminum. And then we move on to our wrought aluminum. So on wrought aluminum, you can use more aggressive cycles compared to the cast. They're not as porous. They're typically highly polished, highly machined. Once again, we recommend on these alloys to use on the wrought aluminum to use a double zincate, because it helps us with our zinc formation, the fine grain layer, which then affects the good deposit of EN on top of it. There's a wide range of Desmuts for these things, nitric fluoride that I went over earlier, and we use a strike, once again, like the cast. So if we go down to our cycle we have for our wrought aluminum, once again, we have the IsoPrep 740. As I said, this is it's a very good cleaner. It has a wide operating window. We can use it for all types of alloys. It works very well for all of them. Once again, we come out of there, we go into our METEX aluminum acid etch. We come out of there, we go through, instead of going now through a triacid, we like to go through a Desmut Deox IsoPrep 184, which doesn't contain a lot of acids. It has a very, 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 very small amount of nitric acid in it, but it's very small. So this is a very good sustainable solution to use. It reduces the amount of nitrics or sulfuric or any of the other acids that you would have in your system. Once we come out of there, we go into our Bondol or our aluminum, our Zincate once again. Then we come out of there, and then we go into where we strip off the Alumon or the Bondol. We go through either nitric, or we go through a product that we like to use, which doesn't contain nitric, which is LPrep 291. This product works very well, and once again, it's a sustainable solution. It doesn't contain nitric acid. So if you're looking to get away from using nitric acid within your facility, this product will be very comparable or even better than what you're using now to do that strip off of that first Zincate. Then we go through the rinses into our next Zincate. Once again, we apply that, rinse it, go through our end plate AL100, rinse them, and then go into the subsequent EN that you need. So that being said, that is what we recommend. Those are our preferred cycles. And I would like to thank you for your time. I know I went a little bit over. It was 44 minutes, but we had booked an hour. And now I would like to give it back over to Rob.
So John, thank you very much. We do have some questions for you. However, there are only 3 of them, so I will just read them to you, and it's probably best you can just leave your last slide up and we can go through them, if that's okay with you.
Okay.
So one of the questions is, what happens when we do the strike after zincating? What is the process? What happens to the zincate that's on the layer?
Oh, the Zincate actually, well, okay. So the Zincate actually is dissolved. Some of the zinc from the Zincate is dissolved into the strike, and it's replaced with nickel. So there's actually a layer of nickel that's formed on top of the Zincate, but some of it is removed. So it is dissolved within the alkaline strike. That's why a lot of people like to use the strikes, because it protects their main bath from getting that contamination of that zinc that's dissolved off the surface.
Great, John. How long can parts be kept after pre-treatment and before Electroless nickel or another plating process? So I'm assuming this means after zincating, how long can they stand out before you put on the Electroless nickel or anything else?
Yeah, that's a very good question, because I have seen at a lot of different facilities where they take after their Zincate, they put them in their rinses and they let them sit there until space becomes available in their EN. My preference is to get them into the Electroless nickel as soon as possible. I think that's where you get your best performance, your best chance for success. I really don't have I can't just say up to 24 hours, or, I don't really have a set time. From my point of view, any time over a couple minutes getting from once you're going through your rinses to your EN is a problem. You don't want to give any chance for, even though you do have a Zincate on that surface, it does have the ability to oxidize. So the faster you can get it from your Zincate through your rinses into your EN tank is the best process that I would recommend. I have seen people leave them in there for a couple hours and they still get good quality out of the end, but I wouldn't recommend it.
Great, John. And then one final question. What is live entry?
Okay, so live entry means that you would have current on the parts before they go into the solution. Typically what would happen is if you were using an acid nickel strike and you were taking your parts and you were putting them into the strike before you go into the electroless nickel, the acid would dissolve off the zincate before you were able actually to get a deposit onto the surface. So that is actually having current on the parts before they go into the strike.
And John, two more just flew in. So I'll
What's
get those to you. I got two more questions for you that just came on the wire.
Okay.
Which is the better Zincate? A cyanide-based or a non-cyanide-based product?
I like to use the cyanide-based. I've just found more success with the cyanide-based Zincates. As we know, cyanide is a very good product that's used in cleaners and things. It really helps make sure the surface is clean and active. I really like to use the Bondol or the Aluman product for the with the cyanide in it.
Okay. This customer wants to process copper plating at 200 microns, and they want to know if it's possible. Also, if you post heat to 200 degrees for 2 hours after plating.
Can you say that once more again?
So instead of electroless nickel, they're going to want to put on copper plating, and they heat it to 200 degrees for 2 hours as a bake after plate.
Yep.
Will they have any issues?
Going into the subsequent steps?
In other words, after baking, are they going to just have any adhesion issues or anything like that with the copper to the substrate of aluminum?
Typically I haven't seen issues with that. To be completely honest, I don't see a lot of people putting the copper on first. I see them putting the nickel and then copper over the nickel. But I mean, if it's done correctly, you shouldn't see any adhesion problems between the strikes in the aluminum.
Okay. Fantastic. Well, thank you, John. Great presentation, as expected. We appreciate everybody taking the time to hear John's presentation today on the sustainable pretreatment for aluminum connectors, especially in aerospace. If you have any further questions, please email John directly at the email you see on your screen. This session will be available on our website. There will be links to them. We will email all of the participants today with them once it becomes available. Again, thank you all very much. Stay safe out there and enjoy your day.
Thank you, everyone.